for double displacement reactions, when you encounter them, you'll know that you have by the fact that you've got two reactants, both of which have something that's a cation and an anion, um, or could potentially be in the case of weak acids and bases. So those are the things you're looking for. The different products are going to be either the result of a precipitation reaction, the result of a gas being formed in the reaction, or the result of an acid-base reaction, which could be a proton transfer or a reaction of a strong acid and base producing a salt and water. Okay, these can be challenging, okay, but as we've done with the other ones, you need to just problem solve your way through them. Sometimes you'll see the spectators right away and you can remove them. Other times you might need to write out the double displacement reaction and then remove the spectators. So for this first one, you've got manganese 2 sulfate and ammonium sulfide, okay, which are, manganese is Mn and the charge on it is 2 plus as given by the formula. So you've got Mns plus ammonium sulfide. Ammonium ion is NH4 plus and sulfide is S2 minus. So the ionic compound is going to be NH42S. Now when you look at what's going to be produced here, sorry, this is sulfate, this is SO4. What's going to be produced here, you're going to get MnS and then ammonium sulfate. So looking at those double displacement products, there's no acid-base reaction happening here. So what you want to look for is a potential precipitate. Ammonium is one of the solubility rules where it's always soluble, so the precipitate here is going to be the magnesium sulfide. So we know immediately that these two are the spectator ions. So what we have here is a reaction between Mn2 plus and S2 minus to produce the MnS. Okay, with this next one, we've got copper 2 sulfate and barium hydroxide, so CuSO4 plus barium hydroxide. When we look at the double displacement, we're going to be looking at copper hydroxide and barium sulfate, both of which, based on the solubility rules, are precipitates. So our products are actually both going to be solids, but the reactants are actually solutions. So when you're writing out the reaction, because these are soluble salts, you need to write the ions. So you've got copper 2 plus sulfate plus barium plus hydroxide, and I'll worry about the balancing in a minute. And I've got barium sulfate is one of my precipitates, and copper hydroxide is the other precipitate. So the only balancing I need to do is to put the 2 there for the hydroxide. Now with these reactions, you'll notice that although you need to know whether it's aqueous or solid, you don't actually need to report the aqueous or the solid. The next one here, equal volumes of equimolar solutions of disodium hydrogen phosphate and hydrochloric acid are mixed. These phrases here, equal volumes and equimolar solutions, are clues to the fact that you probably are dealing with an acid-base reaction. So equal volume, so you can imagine a volume if you wanted to. Equimolar, that means that the solutions are the same concentration. So what we want to do is analyze what we've got here. We've got disodium hydrogen phosphate, which is actually a salt. Okay, so it's Na2HPO4. And then we've got hydrochloric acid, which is a strong acid, or HCl. So one of the products is going to be sodium chloride, if we think about this as a double displacement reaction. So we've got sodium chloride, which is going to be soluble, so it's going to be a spectator. So really the reaction that we have here is between the HPO4 2 minus and the H plus. Okay, it's really just a simple acid-base reaction. The proton is being accepted by the hydrogen phosphate. Okay, and you're left with dihydrogen phosphate. And the sodium chloride are your spectators. Next one, ammonia gas is bubbled into a solution of acetic acid or ethanoic acid. So ammonia, you need to know that formula. Okay, it's a popular one from the acid base unit, so that should be okay. And then ethanoic acid, you've got two carbons and it's a carboxylic acid, so it's CH3COOH. Now, if you look back at your notes, you'll be reminded that the only things that we dissociate or break up into their ions are strong acids and bases and soluble salts. So in this case, because the acetic acid is a weak acid, we're going to keep it in its molecular form in this equation. Now what you need to do is recognize that you've got a weak base and a weak acid here, so it's going to be a proton transfer, and what you're left with is NH4 plus and CH3COO minus. There are no spectators to be removed because of the molecular nature of these reactants. Next one, we've got excess hydrochloric acid being added to a solution of potassium sulfide. Okay, and this is one of the ones that you want to recognize here. Okay, we've got hydrochloric acid plus K2S. So you're going to have hydrogen sulfide and potassium chloride. Okay, this is a strong acid, so it dissociates completely. This is a soluble salt, so it dissociates completely as a reactant. Okay, and the product KCl is also going to be soluble. So the spectators here are K and Cl. So what you actually have here is H plus and S2 minus forming H2S. And this is one of the gases that you want to recognize. So when you've got an acid plus a sulfide, you're going to produce this gas H2S. Okay, this actually smells like rotten eggs, okay, which is a little tidbit that sometimes comes up on the AP exam. Solutions of ammonium sulfate and barium hydroxide are mixed. Okay, so you've got NH4 plus and sulfate, and then the barium hydroxide. So this is a classic double displacement reaction. We're producing ammonium hydroxide and barium sulfate. Okay, the barium sulfate is a precipitate. Okay, and the other thing that you want to see here is that NH4OH is one of the substances that you want to recognize as undergoing a further decomposition. NH4OH further decomposes into ammonia and water. Okay, so what you have here, we've got our ammonium sulfate, so you've got NH4 plus sulfate, okay, and this is also a solution, so it's Ba2 plus 2OH minus, and our products here, we get a precipitate of barium sulfate, and then we get NH3 and H2O. So all of our products are molecular or ionic precipitate here, so they stay together. And to balance this, we need a 2 here. Okay, and that's it. Okay. This next one, we've got acetic acid, which is our ethanoic acid. So in the reaction, it's going to be molecular, and we're mixing it with sodium bicarbonate. Okay, and sodium bicarbonate is NaHCO3. Okay, so I'll put it on the side over here so we can analyze the spectators. So what we're going to have here is a double displacement reaction. So we're going to have the HCO3 combining with the H plus, okay, and then we're going to form sodium acetate. So the sodium is going to be our spectator in this case, Okay, and one of the products is H2CO3. And we must recognize that just like NH4OH, it further decomposes into H2O and CO2. Okay, so in this case, the sodium being the spectator, okay, I'm reacting it with hydrogen carbonate. I get CH3COO minus, my acetate ion, and then I get H2O plus CO2. Next one, dilute sulfuric acid is added to solid calcium fluoride. Okay. In this case, because the sulfuric acid is dilute and it's a strong acid, I'm going to break it up into its ions. The solid calcium fluoride, I simply can write the formula for it. So in this double displacement reaction, the hydrogen from the acid is going to combine with the fluorine, and the calcium is going to combine with the sulfate. Okay. Calcium sulfate is not soluble, so it's a precipitate. Okay. And then the HF that's formed here, hydrochloric acid, is a weak acid, so it also does not dissociate. Okay. And that's all we will cover for now in terms of double displacement reactions. As you can see, there's a great variety. There's different approaches, so you can write it out completely, okay, or you can do some predicting and simplifying. Okay, how you do it is going to be up to you. You want to create a consistent approach that's going to work for you. Okay, and practice, practice, practice.